In today's repetition course, we will have a look at how to solve a problem with the drawing of mesomeric structures and how to avoid mistakes. So here we have a molecular structure of toluene, and toluene is protonated. The question is, where is it protonated preferentially? To solve the problem, we should just go ahead and protonate in ortho position, then protonate in meta position, and then protonate in para position and draw the mesomeric structures. When you are drawing that, please add both hydrogens that are sitting here then. Here one hydrogen was sitting, and by protonation there is then a second hydrogen. As we will see, this is important to avoid mistakes. So then we have a cationic charge here, alpha to the CH3 group, and we can draw two more mesomeric structures. Electron density might migrate, and we could also draw those structures with a positive charge here and there. Similar in that case, let the electronic charge migrate to this and that position, and here you can let it migrate to that and that position. We know the truth is in between all those mesomeric structures. So how to decide which combination is the best one? Well, in this case and in that case, we have a mesomeric structure where the positive charge is located alpha to the methyl group. It is a positive charge at the tertiary center, and only here the CH3 group can participate inductively for the stabilization of a positive charge. So, as we know, tertiary cations are more stable than secondary. So, this is therefore better than that. With the protonation in meta position, we don't get any tertiary carbocation as mesomeric structure. So, protonation in ortho or in para position is therefore preferred. This has been experimentally proven. Toluene was led to react with trifluoroacetic acid, a deuterated one, at 70 degrees. Then the deuterium is transferred to the ortho and para positions preferentially. Well, they made the experiment and found out after a while at 70 degrees at the CH3 group there is no hydrogen deuterium exchange. The ratio at the other positions is 500 to 4 to 450. Please keep in mind, for the 500 we have two ortho positions, but for the 450 we had only one para position. So the para position is slightly preferred compared to the ortho position. So now to the mistakes. Here are some mistakes I have found during discussions with students. Well, if you avoid to write down both hydrogens, that can easily confuse you. So, with such a bow with a cationic charge, this symbolizes those three mesomeric structures, but here's a mistake. So, in this case, it is meant that at this position are the two hydrogens, and here they have changed to the other side. Well, this is not a mesomeric situation. One hydrogen has moved from here to that. So, not mesomeric change, but it is a tautomerization. The same here. Someone thought that if the positive charge moves from that alpha position to the beta position, this would be a situation of mesomery. No, it is not, because in that case one hydrogen has to hop from here to this position. Again, this is a tautomer, not a mesomeric structure. And here someone had the idea, well, was remembering something also with mesomeric structures to a functional group. Well, this is the case, for instance, for a methoxy group or an amino group with a free electron pair, but certainly not with a CH3 group. Has written a double bond here, but had luckily in mind that the carbon can only get 4 bonds overall. Therefore, one hydrogen has to be skipped from 3 hydrogens to 2 hydrogens. But this is also not a mesomeric system. Well, it is a deprotonation. This would resemble a deprotonation at the CH3 group, forming exocyclic double bond, which is certainly far less stable than deprotonating here and going back to the aromatic system. So please avoid such mistakes simply by writing down those hydrogens at that position where the reaction takes place. Thanks for listening.